Okay, hello and welcome back to Data Science Castnet. I'm back from a bit of an extended holiday and break, and so I thought to ease back into things, get back into the mindset of doing data science, machine learning, etc. It might be fun to start with a couple of machine learning contests. This is a nice, easy way to get a problem that's already been framed for you, the data's already been gathered in many cases, and so it's a really nice way to just practice those modeling skills without necessarily having to worry about figuring out a new project, coming up with a premise, etc. So I've loaded up mlcontests.com. It's a nice aggregator, pulls from all your favorite competition platforms. And so today is not going to be necessarily full solutions to any one of these. It's going to be a long video, fairly informal. I'll just record as I come to anything interesting. But instead what I'm going to do is try and find a couple of these that interest me, show you my first steps when looking at a competition. You know, what am I looking for? What sort of approaches am I thinking of as I see what the data looks like? Where do we start? And then, depending on how these go, they might turn into future sort of more focused videos where I'll go from start to finish on the competition with a full solution. But for today, it's just going to be exploring, maybe getting in like a baseline submission on one or two of these. So without further ado, let's start going through. I'm kind of like a big fan of these smaller platforms. I enjoy Kaggle in some ways, but because it's high prizes, high stakes, they tend to be hundreds of entries, very much just competing for that final tiny sliver of advantage. Whereas some of these lower platforms, smaller prizes, but also just a much more fun sort of small community feel, and a lot easier to be up there and high on the leaderboard, and feeling like you're, able to get noticed. So I have a major bias towards Zindi, AICROWD, even driven data to an extent. So the first one that stands out, I know these blitzes are nice short competitions, and generally multiple like sub-problems within some particular focus. So this one is faces, let's see, sentiment classification, age prediction, mask prediction, face recognition, and face deblurring. And what's cool is that this kind of gives you like a little microcosm of various different like image tasks that aren't just image classification. Right, you've got classification, I suppose, facial expressions, but then also kind of regression problem. How old is the person? Bounding boxes, recognition rather than like what class is this, recognizing individuals, and deblurring kind of image to image translation. It's a really fun way to get into some image tasks. I'll keep this one open as a possibility. The other thing is, because these are these short blitz competitions, I think they run over a couple of weeks, but I usually try and cram them into a day. It's just, it's not going to be anything too crazy, but it's going to be a nice way to test your skills, have some fun. Not a huge prize pool, but we're not in it for that. It's just really great to see other people learning. This is very much targeted for beginners, figuring out what these different algorithms are. How do we do bounding boxes? How do we do an image to image, like a unit architecture? If you've never done that before, this kind of competition is great. So I'll keep this bookmarked. We might just do some of these in the background while I'm sort of playing with the data on more like unique competitions. Cool, so that's the first one. When cherry trees are blooming, this is a platform I haven't seen before, George Mason University. So let's check that out and see. I have a suspicion it'll be looking at satellite imagery. I've seen some really cool animations of this kind of cherry blooming season moving up and down as the weather changes and so on. So let's have a look at what the data looks like. They've got a project template, that's nice. Predictions by February 28th, so that's in 2 weeks from now as I record this video. That might be, fairly short time scale, but again, because this is not like looking to find one big thing to dedicate tons of time to, it's more just like stretching our virtual muscles. That might be nice. But I want to find out about the data. Okay, so this is interesting. They have the data on the bloom date for previous years, it looks like, and then we'll be able to use any publicly available data, from what I'm seeing, to predict the bloom date for some additional sites. They've given us latitude, longitude, best prediction, best narrative, and it looks like gathering the additional data is onto us. So that would be a really fun one. It's probably going to be a bit of effort to track down, climate sources and things like that, integrate them. So again, maybe a good larger competition, and one that you could use as a template for your own project, right? Maybe you can look at blooming jacaranda trees in Harare and Joburg and Lusaka, right? You can find ways to modify this into your own project, and because you're sourcing all of that data yourself, you're finding the climate data. That's a really nice portfolio project or something larger. But I think for this exercise, I'll skip it. And so, I'm just looking through, and your personal preference may vary. You might be really interested in an NLP project to brush up those skills. You may be looking to learn computer vision, in which case a lot of these will be fun. But for me, I'm kind of a little bit tired of very computer vision heavy ones, which tend to be find a great model or an ensemble of models, train it for a while, get a good solution, So I'm going to be looking through these with a lens to seeing if I can find something slightly different. Total Recall, I know there's indie folks, so I know what this is about already. This is going to be similar to the facial recognition one from the Blitz, but of course not on people, on sea creatures. So that's quite an exciting idea. And that is a type of computer vision that I haven't done before, right? I've done lots of classification, image regression, but I haven't done this kind of like Face ID thing. But in this case, it'll be identifying individual sea turtles based on facial images. So that might be quite a fun one. Let's see, what's the data like? Labeled JPEGs from different perspectives. So again, that's suddenly taking this from, I throw an image into FastAI's largest model, right, DenseNet, or whatever the latest one is, train it to some default classification objective, and then I'm done. No, we've got different views. We've got lots of different distinct identities. They've got a tutorial collab to get us started. So this is a good candidate. This is one that this looks like it might actually be really interesting. We've got nice labels and all the images that we can pull, a nice link so that we can get that directly into something like collab. So I'll keep this one open as well as another good candidate. Again, it might be quite compute heavy, but it looks like it'll also be pretty interesting. Okay, so that's good. I just want to look for one more that might be like a different type of data, either NLP or, let's see, we've got an NLP project on Kaggle, and then this multi-agent behavior. Now this might be really interesting. Last year they had the first multi-agent behavior challenge, and it was like mouse interactions with sort of key point data. So if it's the same this year, that's going to be pretty cool. Okay, mouse triplets and fruit fly groups. So we've got multiple channels here. And this is nice because suddenly you're not just taking any of the 1 million image classification tutorials off Google and replicating it, right? We've got a really interesting data set. Triplets of socially interacting mice. We want to frame by frame representation of the data set. Okay. They'll use our representations as input to a small network on hidden tasks. Interesting. See, this is really fascinating. This, I think, will be the one that I'll focus on. I might start with one of the image-based ones as kind of a warm-up, and then while that's training, come and really dig into this data, see if we can understand it and train our own, figure out a way of finding some sort of representation. And there's some really interesting possibilities here in terms of, treating this as a time series task and doing a sort of autoregressive transformer model on it. Or just figuring out different, like maybe geometrical ways of distilling the data down and seeing if those features are useful enough to be a valid embedding on their own. So this looks really exciting. They've got a Slack, give us the data as a big array. So we've got frames, animal, ID, body part, which is, nose, ear, neck, etc. And pixel coordinates. So this might be, this will be one that's really great as like a, more involved on all the data is there for us, but we really have to manipulate it in some constructive ways to get it to be meaningful. And it's really fun to think about what, like the equivalence of something like image augmentation might be for a pixel coordinate based key point tracking system, right? There's lots that you can do there, messing with time, messing with rotations and transforms, because two mice approaching one top right and the other bottom left, that could just as well be the same as top left and bottom right. You know, those might be flippable, or it might not. Maybe there's, I know most mice are left-handed, or at least have some preference. I'm not sure which way it goes. Yeah, so they've given us some tasks. They've given us simple labels, and we can use these to try and maybe like learn embeddings that are useful for these tasks and hope that they transfer over. We can also probably work with generating our own labels, for example, proximity or whatever. I don't think hand labeling additional interactions will be allowed, but we can definitely like automatically generate some additional labels, you know, fast movement or something like that, and see if we can use those in some sort of interesting way. Yeah, so that's a cool set. Let's just double check that there's no more that we want to consider. Happy whale and dolphin identification. That's like turtle recognition, but on Kaggle. Investment returns, time series data. Oh, this one I've seen before, air quality from satellite images and sensor data. So this one I've actually already checked out a little bit. This is potentially interesting if you're excited about trying to get into working with like geospatial data. They have the data provided for you, but it's not nice, clean, you know, here's a database of the relevant readings. It's much more like, here are these giant satellite imagery files, right, with multiple bands, multiple locations, and you've got to kind of get all of the work done to read that satellite data, transform it, find the right locations within it that map to their ground-based sensors, and then build your models. And it's time series based, but you're not allowed to obviously look in the future, so you've got to keep being aware of certain like nuances in terms of what data you're allowed to use to make your predictions. So this would be another good one to look at. My concern with it is like a getting started problem, and just sort of, yeah, like this playing around that we're wanting to do is that it might be, you know, a little bit like focused on the logistics of dealing with satellite data rather than anything interesting on the modeling side, although that'll come later. So I might shelve this as a longer project. I can do it in another video. I know there's always interest when there's geospatial stuff happening. But yeah, might be a fun little competition. There's 5 weeks left, so we've got time. And also because of the difficulty of dealing with this data, I don't think there'll be as many submissions, right? If it was labeled JPEGs, anyone can join. Because it's these crazy like different geospatial formats. I know for the first like couple of weeks of the competition, the best solution was just predicting the mean value, right? Like very few people had gotten past that stage, loaded in some data and been able to build any sort of useful models. So it doesn't look like there's a huge amount of activity yet. I'm sure that'll pick up. And that might also be a fun one. If we can do that, we can maybe, you know, make a really nice tutorial starter notebook and help more people join the competition, and focus on the interesting part, which is the modeling and the predicting, without having to deal with these different Python libraries for reading, you know, raster images and so on. So we'll shelve this as a longer one. I think we might use one of these as a quick warm-up. The turtle recall might be a fun like image, you know, or individual recognition challenge, especially with the different perspectives. I think we'll skip anything NLP for this one, although maybe I can do another NLP focused version of this. And then this multi-agent behavior, I think, will be my choice for a more interesting data format. Maybe try out something like the Perceiver.io model that's been around for a little while now, that's designed to deal with this kind of like time series that's not just an image series or an audio, you know, it's like a more like general purpose algorithm. Yeah, or see if we can model this as a transformer task, or just even like my first interest with this one that jumps at me straight out of the gate is, can we make some like sort of hand designed heuristics that are good enough to put us somewhere on the leaderboard as a decent baseline. Yeah, so that looks like a very interesting challenge. I'm going to pause the video now while my Zoom goes a little crazy. And yeah, we'll rejoin once I have got some starter code running on one of those AI Blitz challenges, and we can leave that running in the background while we dig deeper into the multi-agent behavior challenge data. All right, so I'm back after having taken a quick look at what starter content is available for some of the competitions that we shortlisted, as well as just starting to formulate some ideas. So we'll start with the Turtle Recall Challenge from Zindi. Great starter notebook, I'm really impressed. And it turns out that in addition to just being like, here's what the data looks like, here's a quick solution, this is also actually a really great introduction to JAX and haiku. And then at that point it becomes obvious that, oh, right, this is a competition in collaboration with DeepMind, right? These are their favorite tools. So this immediately takes this up a notch from, oh, another one, maybe I can do some interesting things around, face recognition, to this is a really great chance to learn some amazing libraries that are maybe a little bit off the beaten track if you're someone who's used to just using TensorFlow or PyTorch or FastAI. These are some sort of recent, modern, really cool libraries that I don't have much experience with. So suddenly this goes much more into like a learning competition. It'd be nice to like really follow through their tutorial here, get the hang of like, how do we make networks with JAX? How do we train them? How do we do things like image augmentation, which you might be used to from, that's a single line in FastAI or whatever. How do we do that in JAX? What does test time augmentation look like? What does ensembles look like? So this might be a really fun way to get familiar with haiku and JAX, and in that sense it's really exciting to me, but it also is not something that I can immediately start dabbling with like it would be if it was a simple like PyTorch starter code. So that makes this one really interesting, but also one that I'm not gonna just start running right away. I'd rather start diving into like maybe do some tutorials on haiku, read around, run their code, trying to understand like what's going on, and then see if I can start adding improvements, start adding image augmentations or whatever the case may be, and see where we go from there. So really interesting notebook, really great like comprehensive starter code, which I really enjoy, but not something that we can get going with straight away. So that's cool. That's like a nice path to go down. Then looking at the face recognition one here. So they don't have necessarily like a tutorial notebook other than one that just does like, I think it's mean squared error between your candidate image and your possible matches. And also the way it's framed is not necessarily the same as the turtle recognition one, because you're not working with the same set of individuals all the time. You're just working with a collection of, I think, 100 random photographs and one candidate that you have to match. That's going to be the same person as one of these photographs, but maybe a different angle or a different like source photograph. So this is like a nice reduced down version. I guess you would do something like trying to figure out a way of creating some sort of embedding from the image that you can then compare to some internal representation that captures like the features of the face. Again, quite interesting. Not one that we can just dive in, start running a starter notebook and then tweaking and modifying, but an interesting one to examine. But the reason I'm not diving into either of these straight away is predominantly because this MABe behavior notebook challenge looks so interesting. So just to like dive in a little bit more into what the data format looks like, and then the approach that's kind of springing into my head is something I'd like to pursue. So we have these sequences, right, which is I think a minute's worth of recordings at 30 frames per second, so 1800 like frames in total. So this is this like little movie clip of the mice interacting. They've got the key points for each frame where the mice are and some annotations. We're supposed to just submit our internal sort of learned representations for them on the sample submission. And they've given us some public tasks. So under the notebooks tab, there's a getting started notebook made by, I presume, just one of the users of this platform, which is great in that it has some helper functions for downloading the data set, for making little animations with matplotlib of what's going on, for diving into exactly what's going on in this data, how it's represented, and so forth. So let me talk through now. This is like, I've just come to this competition. I'm not going to be running any code just yet. Instead, I want to kind of plan what is my angle of attack going to be on here. And there's a few different like realms that we can look at. So we'll see how I do sketching, but okay, I'm going to have to redo the sketching part. I doodle the whole big diagram, but the audio stopped working when I switched applications. So this is take 2. So in our initial framing, we have the location of these key points, right? The nose, eyes, ears, feet, etc. And they're in this coordinate system, which is just X and Y locations based on pixel coordinates, right? This is from a video. So this makes sense in terms of how the data was gathered, but it might not be the most useful representation for us because we don't really care about, if there's 2 mice down in the bottom corner, 2 mice up in the top corner, the interactions might be the same, but the pixel coordinates are very different. So my first idea is to create a new reference frame that looks at each individual at a time, and then kind of orients the space around where that individual is. So for example, here we could center on this bottom left mouse. I know there's 3, I've only drawn 2 for simplicity, but we can then, for example, start to show the locations of the other mice with reference to that first mouse, right? So now we've got an angle and a distance, and this will help encode whether that mouse is in the other one's field of view, whether it's how far away it is from the mouse, not from some arbitrary boundary of the camera view. Right, so we're taking it from this XY, which is just pixel coordinates, to a different reference frame. And we can also normalize this so that the data is in a more reasonable range, right? Maybe minus pi to pi for the angle, and yeah, figure out some sort of representation here that's based on this new coordinates. And then we can also, within this system, we can do things like say, what angle is the body at with reference to the head, how curled is the tail, how short is the body, is it compressed or extended, and all of this will hopefully be more useful than the raw key point locations in pixel space, because this is now something that's maybe a bit more meaningful. So what this will give us is we've gone from the key points in pixels to our new representation, and we can represent this, you'll have these different values, right? The angles, the distances, the lengths, etc. We can represent this as sort of a feature vector. And this already is hopefully going to be a fairly useful representation, right? Because our hope here is that we've taken it into something more meaningful, and straight away we can turn this into our first submission, right? Submission 1 is just going to be our new feature vector that we've created based on this frame and the key points, but transforming them into something more meaningful for the actual mice, and trying to incorporate more sort of things that we think are potentially useful. So this is all just hand coding. There's no deep learning. There's nothing fancy at this stage. But the hope is that this is already this intermediate representation that's useful enough that we could already send this to their network and try and learn some tasks on it. So that's step 1. Then the next thing that's sort of top of mind for me is that obviously we have a sequence of frames, not a single frame, right? So we have the second frame of the video and the third frame and the fourth frame and so on. So we have this sort of stack here. And with our new transformation, we know how to go from the keyframes to this vector representation. We can then now create that for each frame in the video, right? So we have our representation 1 here, that's frame 1, frame 2, frame 3, and so on. And we can simplify this to say, well, maybe we can treat this as a sequence, right? Each one follows on from the previous one. We'd expect the interactions at time 30 seconds to be dependent on what was happening at time 29 seconds. And so this is now starting to look like something that we could really approach with a modern sequence model like a recurrent neural network or LSTM, or even better, a transformer model, right? So if we can find some way of encoding our frames of the video as now a sequence of representations, let me do this a little bit lower. So we have our sequence here, right? And this is going to be frame by frame by frame. We can feed this into a model, right? Like I said, probably some sort of transformer model, and have it try and predict the next frame in the sequence, right? So we feed in the first frame, then it has some internal representation that it's keeping track of, the next one. And obviously it's kind of architecture dependent exactly what this looks like. But the core idea here is that given some number of steps, we're trying to predict the subsequent step. And we could do these for every frame. We could also maybe space it out, because 30 frames a second is quite high frequency. If we wanted to capture longer range interactions, maybe we could do 2 or 3 frames a second or 10 frames a second. We can experiment with that. But the hope here is that for the model to do a good job at predicting the next frame, it has to be able to learn something about what's going on. And so it's going to see our inputs one by one, like frame by frame, but especially like a transformer model is going to be able to look back. Let me choose a different color. It's going to be able to look back at the previous sort of input, the whole sequence, attend to different parts of that, and then try and make a more informed prediction of, okay, what's going to happen next. And the hope here is that whatever it's learning to try and make this prediction of what's going to happen next will be equally useful for making other predictions, like what currently is going on in terms of, is there fighting or mating, or is there avoidance or greeting, you know, whatever the mouse behavior tasks are. The hope is that whatever this, excuse my zoom, whatever this transformer model is learning will be useful for that. So when we come to make our submissions, we're not going to be submitting for this prediction of what's coming next. We're instead going to be like interrogating the internals of the model to see its internal representation, its learned representation, which it will then use to make those predictions, but which we can also use to make other predictions. So I'm going to stop here. The first step, which is just creating our vector representation, is going to be it's going to be quite time consuming. So I'll check in after that. And then, yeah, once that's done, we can start looking at what exactly does this transformer model look like? How do we deal with the sequence? Are we going to try and tokenize it or quantize it somehow? But that's all for later. For now, we're going to focus on just getting this initial representation, which is going to be already hopefully a decent submission. So I'll check out now, and we'll see you then. Okay, it's been 2 hours since our previous check-in, so I thought I would just show, now that I've actually started playing with the code, what's going on. So the first thing I did was to run a slightly modified version of that notebook that had been shared. This is on the mouse triplets one. Under notebooks, there's a sort of starter one, and just to get a feel for like the submission process and so on. Tweaked how we were getting the sizes, you know, used a large embedding size and made a submission. And I think that's still evaluating, because this is one of the, oh, here we go. Yeah, so we're up there, but not so far, right? Still got a way to go. It's actually slightly worse than the baseline because I've been messing around. But what this has given me is a feel for how long the submissions take, what the process looks like, how to make those submissions through code. So that was really nice to use that notebook just to get that boilerplate done. Now, I've actually started looking at how we were going to implement this sort of modeling step, and I decided to build it around the so-called perceiver architecture. Let me see if I can find a good diagram. Actually, probably here in the Lucid Rains implementation. Yeah, so this is good. So this is based on transformer. The idea is that we have some latent array, right, which is going to sort of model and keep track of our state or some sort of memory as we go forward. And then we have our data coming in sequence, right? And we can use this for classification with sort of outputting logits. We can also go to the modified perceiver IO version, right, which is going to modify this architecture to give us kind of arbitrary output. So I've chosen to start with something that looks basically like the perceiver model, but importantly, we can either do the forward pass and get our output, which in this case is just going to be like the next set of key points, or a set of key points sometime in the future from the current place. But we also have the option to, sorry, ignore, there's lots of code, don't worry about it, mostly copied and pasted from the Lucid Rains implementation. But we can also choose to return the embeddings, which I've set in this case to reduce the full set of embeddings down to one particular dimension, which is this embedding dimension we specify, this latent dimension, right? So we have our latent sort of representation that we want to ultimately use. But to train this representation, we need a task. And so the idea here is to create a little, so downloading the data and create a setup whereby our x is going to be the key points from some start value to some future value, right? A total of sequence length sets of key points. And our y is going to be this look ahead number further on, those key points. So we're just trying to predict the future in a sort of, I guess you would call this, yeah, autoregressive modeling. We're trying to predict 10 steps in the future given a sequence up to a point. And so the model is going to try and learn to do that. And to do that, it's going to learn this set of latents, which is then going to be passed through the final kind of prediction head. But later on, we can just directly pull those latents out. So I chose to specifically like not make a huge data set to start with, right? I'm just messing around. So I'm going to take a sequence and then the Y value, which is 10 further, and then I'm going to jump forward a bit in the larger sequence, take another short sequence, take the Y value, which is a little bit further on, and then jump forward again. So by adding this stride, right, if we made this smaller, we get much more data, right? Much more versions as we move along the sequence step by step. So setting that quite high keeps the data quite small for initial testing. Likewise, I said I don't want every frame, let's take every third frame. That's what this little KK variable does. And yeah, I chose a sequence length of 120. All of this is completely arbitrary, right? I haven't played with this problem much yet, so I'm just sort of thinking, okay, let's do this in, let's see, 10-second chunks or whatever the math works out to be at 30 frames a second, taking every third frame, so that's like 10 frames a second, 120 is 12 seconds, right? So it's all completely arbitrary. I can come back and change all of this later, and when I've got time, once I've validated that everything works, I'll probably come back, lower the stride, maybe add some augmentations, do all the other stuff I talked about. But for now, I'm just throwing in the raw flattened key points for all 3 mice. I'm scaling them down to be a sensible range, but I'm not otherwise pre-processing them at all. Yeah, so we get our training data that looks like, you know, we've got roughly 10,000 training data points, right? Each one is going to be 120 steps. That's like the length of our little sequence times 72 key points, right? So it's a multi-dimensional input, but Perceiver is built for that kind of thing. And our Y value is going to be just a single set of 72 key points for 10 frames in the future. So that's the sort of setup. Turn that into data sets. I'm just using a sort of training loop from Andrzej Karpathy's mini GPT implementation. I just was familiar with that training loop from other projects, and I knew that it was like a nice baseline. Yeah, so we specify our training configuration. We feed in our train and test data sets, and it doesn't take long at all because our data set's really small here, about a minute. But you can watch the train loss sort of gradually get a little better. So it is learning something. So that's training the model for this autoregressive task. The next step, which is what's currently running here, is to say, okay, now I want to take those embeddings. So once I've fed the sequence through the model, what does its latent embedding look like? I set the size to be 100. So here, this is like the submission code basically copied from the notebook that was shared. But in this case, every so often, I'm just taking a sequence, the same sequence length that I used to train the model, passing it through, and then grabbing the embeddings just before the final layer, right? So I go here, model, I feed in my sort of X point, but with return embeddings set to true, so that instead of getting the predicted next points, I'm getting the embeddings instead. Like if you look at the model architecture, let me go up to my perceiver definition here. Yeah, when we're doing the forward pass through this model, there's all the position encoding, self-attention, cross-attention, and then normally when you're making your predictions for the whatever sort of thing you've set, but in this case the future steps, you would run this through this final layer, which is just I think a layer norm. Let's find it here. Self.toLogits, yeah. So reducing the latent dimension down by taking the mean, then through a layer norm, then through a linear layer, and then spitting that out. So instead, what I'm choosing to do is just the reduced part of that. So taking our embedding, which is, I think by default, 256 by 100, and shrinking that down to just a single set of 100 values, which is our like compressed latent representation, right? And that's what we're going to make our submission with. So let me just scroll down. I think it's still running, still got a while to run. So I'll pause again. I just chose to make the video because I was waiting for this to finish. Yeah, the other final confusing thing, obviously I could do this moving forward 1 frame at a time, but that would be incredibly time consuming because this is actually a really large data set, right? They've obviously taken a very large number of recordings, which is great. But yeah, feeding that all through the model 1 at a time would be really painstaking. I could obviously optimize that. But instead for now, because I know the labels aren't going to change that much, I'm just choosing to go, every 100th frame, recalculate the embedding, and then apply that to the next 100 frames. So obviously this is not perfect, but it's better than nothing. And this also, like, this model was trained on a very small subset of the data. At the moment, all I'm doing is just validating that the sort of idea works, that the submission format is right, that the model runs without errors, that's why this is 2 hours after the previous segment. Yeah, and then we'll see what we score, and hopefully it'll be like a non-horrible score. Like, I'm expecting it not to beat the baseline, but maybe to be, somewhere in that same ballpark, rather than, getting something like, oh, sorry, you scored infinitely badly, you fail. So we're going to, see if we can get up here on the leaderboard, and then from there, it's just a matter of saying, okay, now that I've done that, now that I've learned some slightly bad representation, let's see how I can improve that. And that will be pre-processing the data, that will be experimenting with sequence lengths and what type of task, how far in the future we try to predict, whether we can derive other labels that we can try and predict in the future rather than just the key points, and so on and so forth. But at least this gives me like a nice starting point. And this is also, to be honest, like a good place for me to stop once I've made the submission, and then maybe rerun it, training the model for slightly longer to see if that improves things. It's a nice place for me to pause, probably rewrite my whole notebook, add explanation, documentation, make sure that I'm not running any cells out of order. Yeah, so once this is done and I've made my submission, I will record another video showing the score, and then we'll jump ahead in time to later today once I've tidied everything up and made it a lot neater, so that my next phase of experimentation is starting from a really good starting point, rather than the current messy notebook with copied and pasted definitions and so on. So we'll jump ahead to the score now. Okay, it's the next day. I promised we'd jump ahead to the score. So this isn't actually the submission that you saw in progress when I ended the previous recording. That one did okay. Well, I had to make some modifications. That one did okay, beat the baseline, but the next one jumped straight into top position. I think the leaderboard will have updated now, but it was already significantly above the other participants, and higher F1 score, beat the baseline. So that was great. That was a good validation of this approach, because that was with no feature engineering or handcrafting any features, none of that. Just simply using this perceiver model, this transformer model, to learn some sort of latent representation for this task of predicting the future. And that in and of itself, and I didn't even use a very large embedding, I think I tried 20 and 40. That in and of itself was enough to imbue that embedding with useful information for the downstream tasks. So that's a promising start. The power went off soon after, so I didn't have that long and I didn't do any more recording. But what I did do was take my messy notebook, neaten it up. You can see there's now a table of contents. Everything's a lot more sort of standardized. I've got nice functions that made it really easy to redo the same sort of approach on the flies data, right? The flies sub challenge is actually very similar, but in that case, instead of I think it was 12 key points on the mouse, we've got a slightly larger number of key points on the fly plus some extra data. But what I did is just pulled a subset of that, treated it in very much the same way, right? We have a sequence of frames, and then we're trying to predict n frames in the future. And the fly data is at 150 frames a second versus 30 frames a second, and there's some other differences. So very much haven't explored the space of what should my sequence length be, how far ahead should I be predicting, any of that. It's enough that this validated the approach. So we've got a tidier notebook to start experimenting from. All split it up into sections. I've given myself little notes. I also have an ideas section brewing where I've got, things to try next. So that was a great place to end. That's where I ended the day. Nice to be up at the top of the leaderboard. And so this morning, now coming into it again, it was time to stop just treating this data as arbitrary data and not really looking at it. So I had, you can see these little diagrams trying to figure out what the different key points meant, and then coming up with a list of heuristics. So body angle, body length, the separation between the mice, view angles, that sort of thing, just sketching out a little to-do list for myself. The idea being here now, from the 72 key points or whatever, we're going to craft a frame-specific set of more useful heuristics. And so that's what I was doing in this notebook with the title EDA. Just functions like, okay, I would like to, given all the key points, run through each mouse, create a vector between that mouse and the center, store that length, and then take the mean of those lengths, right? And so exactly what it says in the tin, the average distance from the center for the mouse. And that's one of my heuristics. The others are things like speeds, right? Difference between this frame and the next frame. Things like the view angles from one mouse to another, right? How far off my sort of forward axis is the other two mice. So I can combine all of this together and I end up with this sort of metadata array, right? These crafted heuristics, there's 20 values in total, times 1800, so it's 20 values per frame. And I thought it would be interesting, before I use this now for the modeling or for any downstream tasks, what if we just submitted this as our predictions, right? As our embeddings in quotes. So I did some scaling to pull them into a standard range, just because I know I don't know what processing they're doing for their neural network, so probably better to have it in a kind of reasonable range. So standard scalar, and then just for every sequence in their sort of test set, the ones that we need to make submissions for, grab the key points, create our sort of metadata from that, scale it so that it's in a reasonable range, and then submit that as our embeddings, right? And sure enough, this works as a submission, uploaded it, and actually this does better than anything, right? So remember, my previous best submission was I think a border score of 18, tie with second, and mean F1 score of 0.128. This just purely handcrafted set of 20 features that we've hand engineered. This does better than that, right? And so this is now the top of the leaderboard, and that's a good signal that there's some really useful information that we've managed to extract here. And this is kind of an interesting point, because on the one hand, like my tendency and a lot of others is to say, no, the reason we have deep learning is so that we don't have to hand engineer features, right? This seems to make sense, and in the one sense that's true. With a good enough model, we can generally have it learn, more useful representations than anything we can create. But in the other, in a case like this, there's some very obvious, not obvious, but there's some useful things that we can deduce when we know what's causing the data, right? We know that the reason that there's this data in this format is because it's tracking key points on mice and they're interacting, and it's from a video. And knowing all of that, we can craft some features that kind of help the model along. And in this case, just those features by themselves were really, really useful for the downstream tasks. So this is a great place to be, because there's no reason we can't use these features for our modeling. And there's also no reason why we can't restrict our embeddings derived from everything else that we do to, say, 80, dimension 80, and then include our 20 handcrafted artisanal features as the final 20 value. So there's no reason we have to stick to one method to create this embedding vector that we submit. So I'm pretty sure if I combine now the dimension 40 embeddings that was my previous best, and this dimension 20 embeddings that's the new best, pretty much guaranteed that that'll rocket the score up. I don't need to do that just yet because I'm already in first place and we don't want to give other people too much motivation. But it's a nice thing to say for the end. I know that I'm almost certainly going to be able to give myself an extra boost of performance just by adding these extra 20 values. So that's a nice thing to have in the bank, right? If the competition heats up right towards the end, or if I'm struggling to find any other improvements, I know I have this guaranteed bump. And it's nice to have a few of those in your pocket. So little insight into my thinking there. The next steps is going to be going back to our perceiver model and retraining it on these autoregressive tasks, but using now our handcrafted features as well, right? There's no reason I can't use these to feed into the other model. I'll see how that does. And then also starting to investigate the additional tasks. So they specified some extra labels, excuse me, I'm trying to find the right one here, these public tasks. And it was my initial read that these were only to evaluate our embeddings. We weren't supposed to use them, but I asked on the forum, and it turns out that actually it's totally fine to use those as well. They're really just interested in, can you find flexible, interesting new ways of extracting representations? So that was one of the, I think this is the the competition organizer chimed in and said, yeah, that's totally fine to use those. So what I'm actually planning to do, one of my other little post-it note plans that you won't be able to see very well, is divide up my embeddings into some that are derived just from the autoregressive task and the model that's been doing that. Some that are derived from models trained explicitly on the 2 public tasks, and then some that are derived from my handcrafted features, some that are like positional encoding and other tricks, and put that all together into this dimension 100 vector that's hopefully going to be like very, very useful and powerfully predictive. But yeah, good to know that these competitions are always organized by people who are thinking and excited about the topic. So it's nice to ask if you've got questions, and often they'll like come back and be very excited about your ideas. It helps to clarify things because it might be obvious to them, but not to the participants. So, chiming in these discussion forums is a good way to help out your fellow competitors, and also just to clarify. So she says, yeah, therefore you are allowed to use the provided demo labels as well as any other weak signals you design, right? So that would be like my forward prediction task. But you could just as easily try and predict the speed from the key points. So pretty much anything goes with the data that they've given us other than manually labeling, and we know that. Like I said, next task is to kind of integrate this experiments that I've been doing this morning back into my main approach, and see if there's any other ideas. I've got a whole list of things that I can trying to implement augmentation, trying to play around with how far ahead we're doing the prediction for the autoregressive task. Just messing around with combining different versions of the embedding, fine-tuning it on different tasks, and seeing if the fly data needs any different treatment. At the moment, I've kind of been focusing on the mouse data because it's smaller, easier to work with. But these ideas should extend pretty much directly to the fly data as well. Obviously, I need to come up with a new set of heuristics on how to do I read their wing positions, maybe how separated the wings are, are they using their feet to sense things. Got to put my mind in the mind of the fly. So we'll give that a go, and then we'll check back in if I get any new results or an improvement on the score. Okay, so where we were previously, we had just created some handcrafted features, right? Body angles, body lengths, and so on, and made a submission using those and got the best score yet, border score of 14 and mean F1 of 0.135. So I mentioned that our next task was to integrate this back with the previous approach and then go from there. So that's exactly what I've done. The submission that I've just made now takes the embeddings from that perceiver model trained on that forward prediction task, a small position encoding, just a couple of values to encode the position within the sequence that was fed to the perceiver model, this meta array, which is the handcrafted features that I just mentioned, along with a couple of sequence level summaries of those features. And this submission does by far the best yet, right? We went up from 0.135 F1 score to 0.173, and our border score dropped. And this is now the top of the leaderboard by an even higher margin. So I was going to carry on doing further improvements, recording along the way, but it strikes me that this is actually a good place to end the video, because everything from here on is just going to be more sort of manual labor and incremental improvements. We've done the fun part, right? We've done our initial ideas, brainstorming, coming up with approaches. So I think what I'll do is save any future improvements for a review video at the end, one that can be a lot sort of shorter and more concise, going over the competition and the approach. But for now, I think this kind of fulfills the goal of the first, day's worth of working on this problem, getting to grips with the data, coming up with ideas, and starting to implement them. So if you've managed to make it this far, congratulations. I hope you've enjoyed coming along for the ride, and I will see you in the next one. Cheers.